I'm going to take a 10 by 1 by 1 piece of steel like that, and I want to find the natural frequencies of vibration of that. Now, first of all, this is a horrible element to use when it comes to doing a problem like that. When you say beam, don't use solid, okay? So it is most appropriate to do these things with beam problems. But I'm not going to do beams here because I want to explain to you some other issues. The second thing is that when you take your vibrations course in a technical elective, and that may be with me next winter, we do theoretical calculation for the natural frequency of vibration of a simply supported beam. And there's a formula down there. And notice that in that formula, there is E, the material, obviously response of I don't know, copper is going to be different from the response of steel or concrete. There is going to be I, the cross-sectional moment of inertia. In the case of 1 by 1, it's going to be 1 over 12 pH2, 1 over 12. Area and density. You need density. The only time, there's only one case in the last 2 weeks that we ever needed density. Does anybody remember where that was? There was only one case that we actually needed density. All these problems that we have done, there was only one case. Does anybody remember? Yes. Yes, yes. The case of deflecting under self-weight. As soon as you say weight, it's G times density, right? Yes, there was not. But that was a static. However, in any other case where weight is not important, we don't need the density. But as soon as you say vibration, dynamics, mass times acceleration, right? So you need the density. You need the density. So all of these appear in that formula down below, assuming that the ends are simply supported. Now, we can compare our calculation with this to see whether they're in the right ballpark or not. Okay, first of all, what do I mean by natural frequency calculation? So if I have a simply supported beam like this, and if I displace this a little bit and let it go, you know what's going to happen. It's going to vibrate like this, okay? It is also possible for it to vibrate like that. One mode like this, and then turns around, turns around, and turns around. It's going to be tough to do that. Somebody has to hold that middle point fixed and put it in that position, and then let it go, assuming there is no damping and all these things, real life, then it can potentially vibrate like that. This is the second mode. First mode, like this. But also, it can come towards you. The same structure can come towards you, but at a very high frequency. You know, it's going to be very tough because of the fact that the eye this way is a lot bigger than the eye, that way. It's going to be tough. It can also twist, vibrate. It can vibrate as a torsional vibration. It can do torsional vibration or axial vibration. But the one that's very easy to agitate or to create is bending vibration in the first mode. That's very easy. Okay, you don't want to, and these numbers are important because you want to avoid them. Well, why would you like to avoid them? So what? I mean, I get these things. Okay, what do I do with it? What do you say? You know, things like this are the theoretical questions that you will be faced. Some of you, for example, why do we have to worry about this thing? Yeah. Yes. I mean, look, if this was the I-beam, hypothetically, if this was the I-beam in your building, and on top of that building there was an air conditioning unit sitting, and there was a fan or a compressor or whatever turning at a certain speed, if that speed matches the natural frequency, any of these natural frequencies, but mainly the first one, because that's going to be easy to replicate, to cause this thing to, then it's going to vibrate up and down, and you don't want this to happen here. Or sometimes you're sitting in the room and then you hear this noise coming from the air conditioning duct. What the heck is that? So the whole air conditioning duct some component of it, some piece of it, it has a natural frequency which matches some disturbance. And then, of course, that comes to you in the form of a noise, in the form of noise, sound. Okay? All right, now, there is another reason that we want these guys, these natural frequencies. One is avoiding resonance, but there's another one. If you have a structure that is subjected to a dynamic load, now dynamic load means, for example, your fan is sitting up here, it's turning because of the unbalance, this guy starts moving. This is not free vibration. It's vibrating because of that fan. It's not that I move this thing up and let it go. It vibrates, but that's not force vibration, that's free vibration. If you have a unit sitting up here, that causes this thing to go up and down, not in the same shape as the first mode or second mode. All of these are going to be in it, okay? So to predict the dynamic behavior of a structure, one way of doing it, get all these frequencies and learn a little bit more theory, and you can get the dynamic behavior, okay? So for us, it's primarily this business of resonance right now. That's what we want to get our hands on. Now, one thing you want to make sure is that, this is a fact, avoid using planes of symmetry of the structure when you're doing natural frequency calculation. Because if you said this structure that I've drawn here up there has a plane of symmetry, I agree with you, like that. If it vibrates up and down, it has a plane of symmetry. But if it comes towards you, and I insist on that plane of symmetry, I'm kind of throwing away those other frequencies. So be careful. Try not to use planes of symmetry in vibration problems and buckling. You'll see in the second part of the lecture. Okay, because you may be throwing away things that you don't want to. It'll work. It's just that you don't see that. You don't see those frequencies because you said, hey, you can't go out of the plane because of the plane of symmetry, because of the surface layer and things like that. Okay. Now, for this problem, I used that formula down here, and I came up with a natural frequency first mode of about 1500 hertz. Okay, keep that in mind. 1500 hertz from the theoretical calculation from that formula. Okay, let's go ahead and do it. I'm not going to save these things because these are relatively simple problem. By now, the only reason I was saving it, showing file save management, is that because I wanted to make sure that you guys realize that this is something that you have to do on the test. Because if you don't know how to manage these many different problems, many different parts, etc., then you're gonna have a problem. No more for me. It's all yours. So let's start with a part file. And I do suggest, until we do assemblies, try not to use product, okay? Although as long as you know what you're doing, you can use also product. But if you use the product and you're stuck on the test, you're on your own, okay? Okay, on that vertical plane, I will sketch the one by one square, and it really doesn't matter. By the way, I'm going to do this thing two different ways. One of them may be shocker to you, say, why is this guy doing it like that? Or I can do it easier. Yeah, just be patient. This is the easy way. Okay. One. Okay, good. Exit, palette by 10 inches. Good. Make it out of steel. I think it was 10 inches. Yeah. Make it out of steel, metal, steel on the part. Say okay. Good. Now we're going to go to the finite element module. Our part is made, nothing to do. So we're going to go to generative structure analysis. Notice what happens here. We never worried about this box because always the first one was picked by default, static analysis. And every single problem that you have done was static, okay? But as soon as you say vibration, that's a dynamic problem. So do not choose static. You have to use frequency, okay? All right. Now, notice that my load toolbar is dim. There's nothing there. See that? The loads toolbar up there is dim. The restraint is not. The restraint is not. That's because when you're doing frequency calculation, there is no load. You're talking about free vibration, no load. That's why there's no load up there. If I have a static, I have both restraint and the load light up. Okay. And I noticed in the lab, and this may happen to you at one point, is that if inadvertently, whatever it was down here, whether it was a frequency or whether it was a static, whatever, if inadvertently you deleted this, notice that both the restraint and the load are gone. And the question was, what happened? What happened to these? I can't do any more right because you deleted that inadvertently. No big deal. If you want, you can always put it back in. Insert, for example, you can do frequency or you can do static. That's up to you. If I do static, both, that's fine. Both of them light up. But today's lecture is not static, so I'm going to delete this and I'm going to put frequency. And notice that the restraint is going to light up. This is still okay. You understand why? To some people, those things disappeared because inadvertently they deleted that last line. They didn't mean it, but they deleted it. Okay, but that's what I want. Good. There is a mesh there because the other day I noticed that people are saying that, well, maybe it's not working because I don't have a mesh. Yeah, you do have a mesh. That green thing is the mesh. If you want to see it, you go right-click mesh visualization. But the mesh is there. Now, okay, so let's do a restraint. The first way, the more straightforward way, is to say, okay, this end, I'm going to pretend that is a pin. Pin means that doesn't move in X, Y, or Z. So that edge is simply supported. It can still rotate, but it does not go anywhere. Don't do the face. If you do the face clamp, then this becomes a clamped edge. That angle stays 0 degrees. Simple support means the angle. Look at the angle. 30 degrees, 40 degrees. But as soon as you clamp the face, it goes like that. That angle always stays 0. That's not a simple support anymore. That's why I did the edge. Now, as far as this other edge, I told you that sometimes the instructor that taught you made it a pin, sometimes they made it a roller. So let's make it a roller. Now be careful. Roller means not surface slider. The only roller that we know is surface slider. But there is no surface here. I want to take that edge and think about it as roller. So what you need to do is to say user defined on that edge does not move up and does not come towards you. It can still go sideways. That's a roller for that edge. Surface slider is also a roller, but you need a surface. If I'm talking about that edge, you can't put surface slider on. You have to do it yourself, manually. No displacement up and down, no displacement towards you. It can still go in the right direction. And we say, okay, run it. There's nothing else to do. You have the restraint, you can run. No load. This is a free vibration. You say, okay. Done. Can I look at the deformation? In other words, the first mode of vibration should be like this. This is the lowest frequency, the easiest to excite. Okay. Well, let's see. First plot. There's the deformation. There we are. Of course, you can vibrate it too. You can animate it too. Yeah, sure. What is the frequency at which this is happening? Now notice that if I took this and I moved it up and I let it go, this will vibrate in that shape at a certain frequency. Okay, we want to know what that frequency is. So what you do is you double click on this, either on the screen or on the plot that you generated, because everything that's on the screen has a corresponding thing here. You can double click on either one of them. And notice that under occurrences, there's an occurrences tab. Some of these you recognize, but this occurrences tab, it gives you the gives you the frequency. The lowest frequency is 860 hertz. 860 hertz. Okay, so this thing that I did, whether it's right or not, is going to vibrate at that frequency at 860 hertz. What about the next one? The next one is coming towards you at a higher frequency. You can see that. What about the next one? This is the second mode of vibration in plane, like that. Second mode of vibration, sine wave. Okay, at that frequency, if you can manage it, somebody held it here and you brought it to that shape and let it go, it vibrates at that frequency. And then you get torsional and you get, this is a torsional here, look. Okay, all right. So my concern in this problem was the first mode of vibration, transverse vibration. That was the first. So let's go back here. First one. This number, 860, do you remember I gave you a formula? I said I went and calculated these things, it was 1500. Remember that? I said that based on these numbers, I used that formula, and I got the 1500. We're getting 860. So it's very easy to generate numbers. It's very easy to generate color. But making sense out of it is not that, that easy to begin with, okay? So we'll come to that in a second. The other thing is that if you say, okay, what about the displacement? Shape looks like that. Displacement right here. And I can make it look colorful and nice and, you know, all these things that people like. Okay, so mode of vibration, yeah. Okay, how much is that? How much does it deflect? Yeah, 48 inches. The whole thing was 10 inches. This is deflecting 48 inches because when you do natural frequency calculation, the only thing that's correct, the only thing that makes sense is the frequency and the shape of the mode. Deflections are garbage, the stresses are garbage. Actually, stresses we can plot it. It's garbage. The shape and the frequency are important, and they, as long as it's done properly, can be meaningful and correct. Still, we can't resolve why is this thing any different. They're almost double. Why is this thing almost half of what the theory tells me? Okay. So let me go and change my restraint here from a roller to a pin. Remember I said that the instructor sometimes drew both pins for you, and okay. Let's go ahead and do that. So I have two choices. I can just start fresh, or I can clean this one. So I'm going to clean this one. Deactivate. Go to that restraint. Instead of a roller here, basically, we call it a roller, but this is, don't confuse it with surface slider. It's not a surface slider. I delete this, either delete it, make it a clamp, or I can also go here and make this thing all 3 degrees of freedom. That is the same as a clamp. For a solid element, that's the same as clamp. No translation X, Y, Z. I'll leave it like this, okay? Or I can clamp it. Delete it and clamp it. Same thing. For beams, these last 3 are important, and shell. Solids, doesn't matter, okay? So this is the same as clamp. Let me run it now and compare the first frequency of vibration. Good. So let's activate this. Look at the frequency, occurrence. What do you see? What do you see at the first frequency? Almost 1300, almost 1400. That we are comparing it with the 1500 that I showed you. So look, what you do obviously depend on your restraints. Okay, so that formula that I gave you is based on this kind of a condition. Okay, what can I do? Does that mean the formula is right? Does that mean this is right? That's not the point here. Okay, uh, let me tell you that is not the point. How in the world are you going to pick that bottom edge and make it fixed? How do you do that? You have a block. You said this edge is fixed. How can you do that? It's impossible. So this is an assumption that you make. Okay, it happens to match that theory. Both of them are nonsense. There's no way you can take the bottom edge of this and say you have to weld it against something, right? Can you do it? You know, it's impossible. Now, before I do it a different way, same problem a different way. And some of you might say, "Oh, I understand this. I don't know what you're doing with the other one." Oh, okay, be my guest, no problem. You have to see something new. And as far as this problem, whether you do it like that or whether you do it the second way that I'm going to show you, it makes no difference to me. Okay, as long as you do it meaningful way, in a meaningful way, and meaningful means right, right, meaningful way, it's fine. Are there any question before I do this thing a different way? Yes.
So we're provided this context. How should we restrain it?
Mm,
This way?
right, right. So if this problem was given to you on the test without any additional information, you have a choice of, for example, doing the first way, the second way, right? Both of them are okay to me. That's why I'm not going to leave it to you in a problem like this on how to do it. One thing you should not do is you should not plant the face, because if you do that, you're solving a different problem. Okay? All right. So cancel that. Deactivate this block. Okay. I'm going to delete this restraint and delete the con, because I want to show you another way of doing this problem. And deactivate. This is the mesh. Must be the mesh, is it? Yeah. Deactivate the mesh. Okay. So the reason actually the half of this video in the morning was cut off. Up to this point, everything was okay, but then from this point on, it got cut off. Is that I'm going to be talking about something called virtual part here. Show you what this thing is. You have seen it probably. You never knew what it was, and that's okay. I understand that. I'm going to show it. I'm going to do it this way. But then I tried to convince the people that wait. I mean, you have to know other thing. That's because I got an email from somebody that eventually that email ended up in my junk mail, because kind of sometimes these things go there. And this guy was saying that, oh, thank you for your video channel, for your YouTube channel. I use Catia here in this company, some company in Montreal, and we find it useful. And I'm particularly interested about this business of virtual part. There's video on virtual part and rigid virtual part, smooth virtual. So I'm interested. Can you tell me, give me some hand, etc., or give me some information? I'm doing a lot of vehicle dynamics stuff, suspension design, and things like that. And some of the stuff that you did work, some of them I have to need some more information. Anyway, I wanted to show them that email without the guy's name, but then of course the whole recording stopped and he got screwed up. That's why I'm doing it again. I'm not going to show you that. So there is something called virtual part. And the two versions that I'm specifically referring to, one of them is called smooth virtual part, the other one called rigid virtual part. The idea behind virtual part is that, look, you have a specific component that you want to analyze. And this specific component is attached to some other stuff. On this side to something, on this side. For example, your suspension mechanism is attached to the frame of the car on one side and the wheel on the other side, right? So you don't care about the frame. You're not designing the frame. You don't care about the wheel. You're not designing the wheel and things like that. You are interested in the response of that suspension. suspension unit. So what you do, you replace everything on this side and everything on that side with a virtual part, which means that you don't have to mesh things like that because it's really not a part. But the effect of those in the form of a force or a restraint, you introduce it to the suspension unit. Okay? So I can do it with smooth virtual part. Smooth virtual part, let me click on it. I select this end. In other words, there's a stuff there that I'm not going to model. I notice that there is also a handle point here because it could be that right now my handle point, if I don't select it, is going to be that centroid of this cross section. Okay? Otherwise, you can create a point and select that as the handle point. But I didn't do that, so I'm going to be right there. And I do another one on this side. So basically, it tells you that this gadget is attached to some other stuff that I'm not interested in modeling. But I want to model the simple support here, simple support. And if you look at this restraint toolbar, remember there was a gigantic toolbar here with a surface slider. That's the only thing you have used it. The only thing that you have used out of this is the surface slider. But there are other stuff. For example, there's something called here pivot. Isn't a pin just a pivot? This is pivoting. This whole thing is pivoting about this point, basically. Okay, so let me click on it. It says, okay, you have to go and select your virtual part. So it's going to be there. So effectively, it puts a pin for you there. Now, you can change the direction of this 0100. That means this can pivot about, in the x. If you change it to 01, let's change this to 01. There, it looks like that. Wait a minute. Hang in there. Where was this? Where was the pivot? Right there. 01. Okay, so it's coming out. See that? Or you can do it as 01 here. So basically, you can orient this thing any way you want. Okay, but I want it the way I showed it to you, which was a 1 here. You can also do it at an oblique orientation, but 0. Come on, 0, 0, 0. And this is a 1. Yeah. So I have a virtual part here, which is pivot, and a virtual part there, another one on this side to that. Oh, I already had it. Sorry, I wanted the pivot. I wanted the pivot. Not already had created the virtual part. There. So instead of deciding where do I clamp the bottom edge, or or do a roller here, etc., as long as this thing can vibrate like that as a hinge, as a pivot, I can do it like that. It's so smooth virtual part because it assumes that the ends of this block actually can change shape. Of course it can change it. But if you make it rigid, the ends of this block will stay the same size, will not change shape. So which one is right depends on your problem. If this piece was aluminum attached to a steel piece, the steel piece you're not modeling, the steel is rigid. If they're perfectly bonded together somehow, then of course steel to aluminum is going to be rigid. But if it's steel to steel, okay, that I'm not modeling, but this thing can change shape. Anyway, that's not the issue here. I'm showing a different way of doing it using this business of virtual part. And run it. Done. Look at the deformed shape. Look at the frequencies. Occurrences. 866. Yeah, 866. Remember first time the different numbers, okay? The moral of the story is that sometimes there are these features that are buried in there and you can use it to your advantage. Advantage may not be on the test. advantage maybe to your, I don't know, capstone project, or when you get a job, like this guy was saying, you have to do it to make money. Okay, folks, any questions here? A problem like that, if it was presented to you on a test, because I'm not giving you any instruction, any one of these methods would have been okay. Okay. Yes. Oh, you see, you have to look at that 1500 was based on the assumption that, let me put it this way. Here, when I put a pivot, for example, that means that this end, okay, cannot actually shrink. Because notice that there are different ways, different things here. One of them, you can't see it from that distance, but there is fixture here that prevents this thing going back and forth, this way, okay? But there are other ones that are not like that. So by changing those numbers will change, okay? So you might ask, perhaps, what about that 1500? Is that 1500 ultimate truth? The answer is no, not necessarily, okay? So, and what you put here is going to affect, of course, these values. I think that's what you were asking. As I said, it's very easy to generate these numbers. Okay? Now, last time, remember, I put a clamp here, not a clamp, clamp the bottom edge and clamp the bottom edge, and I got almost 1500, okay? But here, different condition. Let's check something, by the way. I'm going to change you can try that yourself if you want. You can change this to the rigid virtual part to see how it affects that 1500 or 860 that I'm getting now. It will change it. Okay. Any other questions? Okay. So let me get rid of this.